Okay, so welcome to this video. Today we are designing the communication subsystem for the CubeSat. Previously, we have designed the onboard computer. We have designed the flowchart for the battery system or the EPS. So in this short video, I'm going to brainstorm, or we are going to come up with the design structure for the COM system. And remember, this CubeSat is just supposed to be very simple for DIY tech demonstration. And so we are not going to use very complicated design architectures or methods. And as such, it's supposed to be low cost but still functional as it's supposed to be. So in this new diagram, I'm going to create a flow chart. Let's say this is a comms system. Comms. Okay, so let's see what is the comms system supposed to do, right? What is it supposed to do? So the first thing it's supposed to do is should be able to receive commands from ground station. I'll call it GS. Okay, but we should be able to send commands to ground station. Number three should be able to process commands from ground station, right? Number four, the communication subsystem should be able to decode commands. I mean, they are almost the same code, but I'll just put it in a different function. Decode commands from a ground station. Number five, for my CubeSat, I want it to be able to send commands to send processed commands to the onboard computer via ISA connector. Number six, the other function of the comms board. Now this is like generic function, but should be able to provide regulated power to IC to the MCU stroke the comms chip. Number seven should be able to provide inhibit switches and yeah, I think for now let's work with that. Number eight, store command logs. So in case you have like frequent commands being sent to and from the CubeSat, we want it to be able to store like a list of all the previous commands that have ever been sent from the ground station and commands that have also been sent from the CubeSat to the ground station. So it should store that data somewhere. All right. So let's work with this for now. Seconds. Save it somewhere here. Save. Okay. So remember, I want this CubeSat to have a dedicated MCU. So I'll have an MCU here, and I want to use the STM32F103. It's very basic because its job is just to receive, decode, and send commands to and from OBC and ground station. So this is STM board. The other thing I want to have obviously is this is the power, or let me call it the voltage regulator, right? So voltage regulator receives voltage from the EPS board, And remember, this CubeSat is using the dedicated architecture. So, which means that you receive 5 volts from this is 5 volts from EPS, right? And then this 5 volts is regulated to 3.3 volts. So receive that, and then this power can now be supplied to that board. So I'm just gonna draw that real quick, sharp, just like that. Okay. So what module are we going to use? So I want us to use a LoRa transceiver. So LoRa is has both the receive and transmit commands. I mean module or ability, which means I'll be able to cut the cost of designing, the cost and the complexity of designing an RF circuit. They'll cut the project workload down by a lot. So LoRa transceiver here. Okay. So there are other considerations that we need to look at. For example, the bit rate, the frequency, the power consumption. But for now, for this flowchart, let's just start here. Maybe our next video we'll be able to discuss those considerations. So LoRa is connected to the MCU via SPI. I want to use SPI here. SPI connection. Now, the other thing I can use is UART, but UART just for redundancy. But if the LoRa module we choose, maybe in the circuit design, it does not handle UART, then we are good with SPI. So I'll put this as dotted for now. And say UART. Okay, so these two are like that. Let's see. Oops. Okay, so LoRa module is right there. STM32. Then the other thing we want to have is, of course, the antenna. So let me place an antenna here. Antenna around somewhere here. Antenna should be this is sharp. Then do it like that. So the work of the antenna obviously is to, convert the electrical waves into radio waves from the LoRa to the ground station. So this is the antenna here. LoRa uses the 468 megahertz LoRa. There is the 933 megahertz LoRa, but we'll look at the okay, so the next thing we have is we should have a flash memory here to store the commands. So remember again, I'm aiming for a very simple board, but functional board, right? So there are no bells and whistles in this one. So these arrows should be pointing both sides, but for now let's work with this, and they should communicate through SPI. Most chips, flash memory chips, use SPI. We have the flash memory, we have the regulator, we have something called the brown out reset external. Is the brown out reset in case the power goes down. We want to reset the MCU so that it always knows its actual state or its real state when the power comes back up. So we don't want it operating at 2 volts when it's supposed to operate at 2.6 or 3.3 volts, right? So if it goes below, let's say 3 volts or below logic level, we reset it externally. We can implement this in software also, but for now, let's work with also a redundant system that is external to the chip. Okay, let me see. The next thing we have LEDs that will be used to that's for debugging anyway for this point for debugging. Let me place it right here, and this is supposed to be like that. Let's say debug LEDs, right? Debug LEDs. Okay. The other thing we have now for like standard specification of a CubeSat is what we call the inhibit switches. Inhibit switches are just basically switches that make sure that the system is off when it's inserted into the launch pad, not launch pad, like the deployer, the CubeSat deployer, and turns the system on once it's deployed in orbit. So mostly they are just momentary switch, not momentary, like mechanical spring switches that are pressed when you insert it into the pod. So they are either normally open or normally closed, and depends on your implementation. But the whole function of them is to make sure the system remains off until it is deployed. So it's recommended to have at least three. Uh, so we'll revise this system, but for now, let me put these two right there. Um, Inhibit switches. What else should we have? The other thing now we have is what we call the ISA connector. Now, I want these commands to pass from to be passed from this STM32 dedicated chip to the onboard computer. ISA connector, right? This is the ISA connector. So let's see. Can I rotate it? Oh, yes, I can. Like that. Yeah. Cool. So I want these commands here. Once they are processed, they should be passed from the comms port to the ISA connector, right? And then from the ISA connector to on the other side, on the other board on this side is the OBC, board computer. Okay, right. So that's that. Now, what's the interface of connecting this STM and this STM here? Because this onboard computer also has its STM32 board, dedicated MCU. So you can configure this as a slave device and this as the master, obviously. So I want to use this as I2C, right? So this should be I2C connector here. Or rather, protocol, not connector. I2C protocol. So this is going to be I2C slave device, right? I2C slave device. Um, okay, cool. I2C slave device. Right. What else might I have missed? Okay, now one other thing that I want to have is something called the board insert detect. So board insert detect is a way of knowing that that board is inserted into the old stack of a CubeSat. So the way you have different PCBs, you have the OBC, the EPS, the comms board, maybe the attitude and determination control board. So the OBC should be able to detect that all these boards are inserted. So it's very easy to do that. what you have is just a resistor here that pulls this board down and connect it to a pin on the OPC. So when you insert it, you just sample that pin on the OPC and you realize that okay, this pin is pulled down, so that board is inserted, right? So just like it's like a switch of some sort. The board insert detect, board insert detect. Let's place it right there. Sharp. Yeah, something like that. Yeah, yeah. So what's the operation like? Again, let's go through this again. So what happens is commands are sent from let's see from yeah. So commands are sent. Okay, I'm gonna move this. Okay, so commands are sent from the ground station, right? Ground station is right here. Commands are sent from the ground station. These commands are received by the antenna, uh, on the onboard computer. Okay, so they're received by the antenna on the onboard computer at this point through a LoRa transceiver. This LoRa transceiver sends those commands via SPI to the STM32 chip. STM32 runs a command parser or command processor that we will design on the firmware side. That command processor decodes the command and sends it to the onboard computer via the ISA connector through I2C protocol. So ISA connector, remember again, is a standard way of stacking boards together, especially for these CubeSats. Now, once these commands are processed here, or rather received, they should be stored on the flash memory. So we can easily retrieve. You can send a command, for example, from the onboard computer to say, okay, now give us all the commands that we have sent for the last 7 days. We can easily read this channel here, right? Now, debug LEDs are basically for just turning on and off to see whether things are working as expected. The hardware side, brownout resets to reset the MCU in case of a power brownout. Board insert detect to detect if this board has been inserted the right way into the stack of the PCBs on the CubeSat. Inhibit switches again they prevent um, the system from turning on before it is deployed. Right? Yeah. So I think this is more than enough. This should be a very simple approach or design architecture for the comms port. And next video we will now design the circuit for this and step by step and see how what the considerations we make for this communication board. So maybe let me add one last thing, a title to this flowchart, communication and command processing board. Right. Save and right. Cool. So that's last. If you have any question, put it in the comments and see you in the next one.